Graphing equivalent ratios. So we've used tables and we've used double number lines to represent equivalent ratios. Now let's look at how we can use a graph to determine other equivalent ratios and understand the connections between the representations. So we're on page 227, for those of you that aren't there yet. Alina. They right away give us all three representations. So Ava creates more rectangles, so this is a continuation of the cutting exercise we did last class, that maintain the same ratio of side lengths. The table shows the lengths of the sides of a set of rectangles. So we have it in table format where we compare the short side to the long side. Then the double number line has the same data. You can also represent the equivalent ratios on a coordinate plane. So let's take a look at this really quickly. As I look at the different formats, I look at the table, I look at the double number line. Is there anything that sticks out to you with the double number line that you don't necessarily really see quickly in the table? Molly?
The number on the top and bottom are equivalent to each other in the ratio.
Good. Is that just one of them, or is that both of them?
I'd say it can be applied to both, but I'd say it's more noticeable because of the lines and the double number lines.
Good. Okay. So the lines of the double number line directly connect them, right?
Yeah.
Or the table just next to each other. Anything else you noticed in the double number line versus the table? Marion? Never mind. Okay. I can do that pretty well. You can ask Miss Michelle that one. He doesn't need a red folder. He's got a module. No, my new person isn't in here yet. She's still being escorted. I'm sorry, Joanne. Okay, they both have the same numbers, right? Nobody noticed this blank space on the double number line? Doesn't that stick out a lot more than on the table?
Yes.
To me, it does.
Yeah.
I mean, that's one of the first things I saw when I looked at this. I was like, wow, we're missing an interval here. But I look at the table, I mean, it's literally just a bunch of numbers. It doesn't really stick out the way it did on the double number line. Now, we can also look at a graphs. Now, I want you guys to look at this, and I want everybody to actually look back just 2 pages. So going back to page 225. This is the same graph you actually have on 225, isn't it? Because this is Ava's rectangle, but they did 2 things on this. Who notices the 2 things they did? I'll give you a hint. One of them has the fact to do there's 2 graphs. Yes? They do. They both start at 0, 0. Good. They changed the intervals. Okay? On your graph on page 225, the intervals on both of them were by 2s. This time they made the y-axis by 5s. So what does that do? That changes the look of our line. So if I draw my line on this one, it's now going straight up through here, whereas last time it was more like this, right? It's the same data, but because they changed the intervals, it looks different. Is it okay that they went by 5 on the y-axis but 2 on the x-axis? Yes. Yeah, that's okay. The whole key is once I start an interval on each axis, I have to maintain that interval. So they started at 5, but then they went up by 5, so that's okay. They started at 2, but went up by 2, so that's okay. It doesn't have to be the same intervals on each one, but once I start an interval on one of the axes, I have to maintain that interval. Okay? What was the other big change they made and why we needed 2 graphs? Anybody see the second change they made? All right. Good. They switched the x-axis and the y-axis around. So bottom line on this, if you're given a graph, you really need to pay attention to everything. We haven't talked about graphs yet, really, but you have a title, you have your axes, you have your intervals, and then you plot the points, okay? So we have 3 different representations of all of the same data. Is everybody okay with this so far? Okay? On the bottom, label the remaining ratios on each graph. So what does that mean I'm supposed to do? What does it mean to label a ratio, guys, on a graph? Madison? Write the ratio. So they did the first 2 for you. All they're saying is write the rest of them. So our next point, so 2,5 is actually that point, 410 is this point. So my next point is what? 6:15. Then the next one is 8:20. Then we do 10:25. Then our next one is 14:35. Now the next ones, anybody notice any similarities, differences? Madison? They just switched the order, right? Does that matter? Absolutely, order matters. 2/5 is a fraction. 5/2 is 2.5. Is that the same numbers? No, because I'm comparing different things. So your order matters. You have to be cognizant of what I'm doing. So now all we need to do really is take those numbers we just did and reverse them. Molly, you getting all this down?
Yeah, I labeled the thing, I labeled the ratios that I had to add on the graph.
On both of them?
Yeah.
Okay. Everybody good on this page? If you have the first graph, guys, literally all you're doing is reversing the numbers for the second one. Okay, 228.
I'm going to take a few people with me somewhere for real pictures.
Okay, consider the question. What rectangle can Ava create that has a short side of 12 units? So, you know 6 different equivalent ratios from the original graph. The graph shows how to use the ratios 2:5 and 10:25, or 2:5 and 14:35 to determine the equivalent ratio of 12:30. So in other words, we're saying what I'm doing is using the fact that my ratio is 2:5. In other words, for every 2 I'm going over, I'm going up 5. Does everybody see that? I mean, it's literally right on your axes. So if I start at 10:25, which is the last point, or the point between the last 2 we did, if I go over 2 and up 5, where do I end up? 12:30. So really what we've done is we've just taken the line that we had drawn through there and extended it and said, okay, once I get to 12, what is my y equivalent? Is this making sense so far? Everybody good?
Not yet.
Okay. So Ava could create a rectangle with a short side length of 12 and a long side length of 30. Describe how to determine the long side length of a rectangle with a short side length of 16 units given each representation. So we actually have all 3 representations for you. Problem A, we're asking you to do it on the graph. Turn the page, or it's actually your opposing page, right? So the opposite side, you've got to do a table, and then they have the double number lines. So they want you to use all 3 representations. Tell me how you can figure out those equivalent ratios. I can give you guys one hint. If you go back to 227, they've already given you all 3 formats. So you can kind of look back at that if you're a little unsure on how it's happening. Okay? So do your best to figure it out on your own or as a table. But we want you to answer parts A, B, and C. We'll give you guys about 6 minutes to do so. Are you okay?
Yeah, she just got that.
Yeah, we did.
Sorry.
Yeah, she took us to see a double rainbow. You should go look in Miller's room right now. It is gorgeous. It's a double rainbow.
That is awesome.
You know we're not paused, right?
Why did you pause? Miss McShann, come on now. As we look at all three different formats, the first one, we kind of gave you the hint on the 35 that we just found, right? What do I need to do? I go over and up. So if I go over 2 and up 5, from the last point I know, which was 1435, you get 1640. Make sense? Now your other option is, if I drew the line like I did already, so you draw this line in here, I can now say, okay, well that line crosses right here at 16, right? So I can go up from 16 till I get to that point, then I go over, and I can see that it is at 1640. Honestly, that's the huge benefit of the line. All I need to do is figure out where it's crossing on each of those axes to figure out what that equivalent ratio is, because every ratio on that line is equivalent to 2/5. Does that make sense for everybody? Okay, so our second option was extend the line to find the point (1640), which you can then turn into that ratio of 16:40. So either of those options are fully acceptable. I'll give you guys a second to make sure you have both these written down, especially since I see several of you who are not writing in your books right now, Ara. So 2 options. Figure out what the pattern was, go over 2 up 5, or extend the line and just figure out where it's crossing at that point. Okay? So that's your big advantage. Miss McShann, he said can. I did. That's why he waited for you to come back. Okay, going to the next one. The table. So I gave you guys the hint of going back to here. You can see the table is set up short side, long side. So we do the same thing. Short side, long side. Okay, now my tables may not look like yours, because all I'm going to do is say, well, I know the relationship is 2/5. I know I want to get to 16. So I show my work. How did I do that? Okay. Now, Miss McShann is not as much of a stickler as I am, but on my side, how hard was it for me to draw that ×8 on those two?
Not that hard.
Took maybe a second? Second? 2 seconds if you're a little slow like RJ?
Maybe a second and a half if you're like medium.
But is that hard to do?
No.
But if you guys show me that, do I understand exactly what your thought process was?
Yes.
No.
Yes, I do. So please, on the tables, do that. Show us your work so that if you make a simple math error, I can still give you partial credit. Because I can say, oh, you said 5 times 8 was 30. You made a math error. But you understood it was ×8. You did it on both sides. Make sense? So again, please show your work. My double number line. I will say this one is actually really cool as long as they've already done all the work for you. Because then all I got to do is add in the numbers that are missing, right? I'm missing 12 and 16. I'm missing 30 and 40. So my personal preference is graphing. Why? Because you're going to find out, especially as we get into more algebra, graphs you're going to use all the time. The graphs are really nice because I can literally look at any point on there and I know it's equivalent to my 2 to 5. My second would probably be the table, because especially if I know exactly where my base ratio is, where I'm going, it's an easy step most of the time. Double number lines are actually my third favorite because there's a lot of work to putting those together. But just a quick poll for you guys. How many of you like doing the graphs? How many think that one was really neat, a good way to do that? The graphs. So I see about 4 hands. How many of you prefer the tables? Well, that looks like just a couple more. How many of you prefer the double number lines? So you can see we have people raising their hand for all 3 of those modalities, right? This is part of the reason we teach you all of them, because all of you are going to have preferences. And honestly, it doesn't matter. All 3 of these work. Now, that being said, you have to follow instructions, correct?
Yes.
So if it tells you, give me a table, and you do a double number line, are you getting full credit? No. But if it just says, find the equivalent ratio, does it matter which of the 3 formats you use? No. Use whatever you feel the most comfortable with. Okay? So, marking your text, following directions, always key, but we're giving you a lot of other options. Okay, going on. One way to analyze the relationship between equivalent ratios displayed on a graph is to draw a line to connect the points. So I kind of got ahead of myself already because that's just the way I do the graphs. You can also extend the line to make predictions of other equivalent ratios. Sometimes all of the points on the line make sense. Other times when you draw a line, not all the points on the line make sense. So when we draw a line through all the points, you plot it on your graph, do all the points on the line you drew make sense in this problem situation? Why or why not? In other words, if I look at this line, does every point on this line make sense given that I am drawing different proportional rectangles? It does? No, it doesn't? How many of you think it does make sense that every point on this line can be used to draw one of the rectangles? Yes, I see about 4 hands. How many of you do not think it makes sense that every point on this line can be used for a rectangle? Wow, we have a...
Thank you, that was an experience.
Was it not awesome?
Appreciate you sharing.
So just so everybody knows, we just saw a double rainbow. Talking to YouTube now. So we actually took a break to go out and show it because it's a once in a lifetime as good as it is. Yeah, saying, oh, you're the one that told her? Thank you. So.
We were Miller, so I looked at Miller, I was like, Miller, there's a double rainbow. And she's like, oh.
Okay, guys, here's the big one. Unfortunately, we have a lot of you who did not make a choice as to whether every point or not makes sense, which kind of disturbs me. So you have to make a choice. It either makes sense or it doesn't. So let's try again. How many of you think it makes sense that every point on this line can be used to draw out one of the rectangles? Okay, hands down. How many of you do not think it makes sense that every point on this line? Okay, we have a lot less on that side. So Molly, why don't you think it makes sense?
Because I don't understand what you are necessarily saying when you mean they're consecutive and double. I would need that to be explained to me. Because I don't understand what the concept is to begin with, so it doesn't make sense to me.
Okay, thank you for that good explanation. So what we're saying is, if I look at all of these points, that means I could make a rectangle that's 2 by 5, and it's going to be equivalent to a rectangle that is 4 by 10, which will also be equivalent to a rectangle that is 6 by 15.
Okay.
So now you're on the side of all that makes sense? Okay? Now I'm going to add a caveat in here, because I don't really like the way they did this graph and put this question together. Why do I say that? For one like this, it actually makes sense to me, right? So what is halfway between 2 and 3? Or 2 and 4? I gave you the answer. 3. What's halfway between 5 and 10?
8.
7. 7.5. So is it easy to figure out what that point is? Yeah. So that makes this very easy to find the equivalent ratios. But what if I go, we'll say right here, at 2 2/10? Can I figure out what's hitting there? Not really.
I mean, you could
That gets really,
very hard.
really bad, doesn't it? Because I'm basically having to do all that math and figure it out because the graph doesn't really tell me, does it? So here would be my answer on this one, guys. Oops. Let me go back to the right one. Do they all make sense? I would say no because of the interval. Because they did the side by 5, it doesn't make sense. But I would add in, however, every point on the line is equivalent to 2 to 5. It's just that with the intervals they use by going up by 5s, you can't really tell on the y-axis exactly where that's intersecting. Had they done it by 1s, I think that would actually have been a really good one. So that's where we have this one. Do fractional values make sense when I'm comparing the side lengths? Not really. Yes, Jamarian? Sign out. Okay, number 4. How do all of the representations, tables, double number lines, and graphs show equivalent ratios? How are they similar? Describe some of the advantages. So we actually have several different parts to this, right? So how are they similar? How do the representations show equivalence? And describe some of the advantages of each representation. So I'm going to put a few up here, and then we'll see if Mr. Chan has some she wants to add in as well. To me, this is the most important question of this entire lesson, because this is really where we get to what is the advantage? How do I do all of this? So for the graph, how does it show the equivalent ratios? Guys, how did the graph show the equivalent ratios? Yes. The points plotted on the line, right? Okay? So every point on that line is equivalent to that initial ratio. That is how it shows it. What is the advantage to the graph? What were a couple of things we just did on the graph that we were able to really quickly show once we had that line drawn? Gosh, it's so fun having them first thing in the morning, isn't it?
Ooh.
Mr. Chan?
If a point does not fall on the line, you know it is not equal.
Excellent.
I know, right? Isn't it like it? It's like your math.
Okay. Now, here is the key advantage to me of the graph, guys. You can easily find points in the intervals, like we did the 3, 7.5, and make predictions. So I can extend the line to figure out other equivalent ratios that aren't already listed. So please write that down. Again, this is probably the most important part of the entire lesson for today, so you need to make sure you have this.
I hate my phone. It does that completely. When it comes in, I'll let you see.
Okay. Okay, the second one we looked at was tables. How do the tables show the equivalent ratios? How do the tables show equivalent ratios, guys? Yes. That's it. The number on top compared to the number on bottom. So where is the key advantage to tables? I'll give you a hint. If I have the graph, do I want to graph all the way out to 100? Why not? Takes too long. If I have a table, can I go from 2 to 100 very easily?
Yes.
So where's the advantage of the tables? With big intervals. Okay? They work best with large intervals. Oh, dang, that is a great picture of the double rainbow. Yeah. Oh, I didn't even notice that part of it. You sent that one to me, right?
No, but I'm about to.
Okay. And our last one we looked at, what would work best with her?
You want her to sit here? Or do you want her to sit?
Have her sit. Who sits with you, Landon? I know Nala's there, but who's across from her? Rian. Yeah, have her sit there. Okay, then our last one was the double number lines. How do they show the ratio? Guys, how do the double number lines show the ratios? RJ? How do the double number lines show the ratios? Jamarian? Guys, quiet down, please. Jamarian was answering. That's it. It's just the intervals on each side of it. The intervals on top and bottom. So what is the key advantage to the double number line? Madison?
It allows you to see how it allows you to see the equivalent ratios easily.
Okay. Going back to our first representation, what did the double number line do that the table didn't? We pointed it out, right? We saw that gap right away. So it's easy to spot gaps, but one of the other big ones on double number lines is it's actually to find intervals in between. It's probably the easiest of any of them to figure out in between because I can figure out exactly what that interval is and how far apart they are. So you can see gaps in data. And good for finding points between the intervals. Ms. McShann, anything you want to add to our list on these advantages or how to see them? That was my favorite question this whole lesson. Okay, so, okay guys, let's bring it back together. Let's go to the next page. We're on 230. Did you want to do this one, Ms. McShann? I got the fan going.
I guess. Yes.
All right, 5, 4. All right, so we have talked about different ways to show equivalent ratios. The graph represents the number of gallons of water used to the number of times a toilet is flushed. So let's look at our graph first. Our x-axis represents the flushes, and our y-axis represents the gallons of water. I'm going to read number 1 and then I'm going to explain to you why I'm emphasizing it. It says, write each point on the graph as a ratio of gallons to water used to number of flushes. When we do graphs such as this and ask you to write the ordered pair, what always comes first? What always comes first when you write the two numbers for a point?
Whatever it said, I'm pretty sure it's whatever it says first. Like if it says gallons of water used, then you put a number.
But on a graph like this, what always comes first? Callie? The X, because it comes first in the alphabet, right? We always tell you the X comes first. You have to go in before you can go upstairs. That's just the way it is. However, they are doing it wrong on this activity. They are telling you to put the Y number first. So after this activity, please forget you did that because it will never happen again. You always put your X number first and your Y number second because that's the order they go in the alphabet. Make sense? Okay, so, but for this activity, you are doing gallons of water to number of flushes. So you are doing it backwards, and you are writing a ratio for each of those points. I'm going to give you about 2 minutes to get those ratios written. We're going to go over them, and then I will give you the rest of the page. So 2 minutes, ratios. 4, 3. Okay, who can tell me what our ratio is for our first point on this graph?
3 gallons of water used for 1 flush.
Does everybody agree? Yes, and remember, this is not how you're supposed to do it. You never put the Y number first. I don't know why they did it this way. Did it drive you crazy too? Oh, I said it every class over and over again. Okay, yes.
The next one would be 6 gallons used to 2 flushes.
Okay, Michael?
9 and 3.
There we go. That's how you say a ratio. And this side, last ratio. Does anybody have any questions about how we made those ratios? Good. You may work as a table. I want you to answer B through E, and I'm going to give you 5 minutes. Go for it. B through E. 4, 3. Okay, so who can tell me, B, what do you notice about each of these ratios?
All of the ratios are equal to 3 and 1.
Yes, they all have the same value of 3 to 1.
Guys, you're at the print, you should be writing it down. That's not in your book.
What's another word for the same value? They are equivalent. All right, C, how many gallons of water would you use if you flushed the toilet 8 times? Lauren? Okay, what method did you use?
I multiplied 4 flushes by 2 and multiplied 12 gallons.
Okay, so you used one of the ratios we already had of 12 to 4 gallons over 4 flushes. And you knew we were going to 8. She says she multiplied by 2, so she did the same at the top and got 24 gallons. Does everybody agree? So you will use 24 gallons of water.
Did she explain her method?
Yes.
Yeah, she showed.
I showed my work.
The work, right? Does that not explain how she got it? Yeah. Guys, that's why you show your work. That carries through that explanation piece.
All right, how many times would you flush the toilet to use 18 gallons of water?
6 times because if 5 flushes is equal to 15 gallons,
Where did you get that ratio? Because it wasn't one of our first ones.
well, I already know that if 1 flush is equal to 3 gallons,
So I'm going to start there. But I see what you're saying. Keep going.
then I would just multiply by 6 for both the top and the bottom to get 18 gallons and 6 flushes.
Good job. So you will flush the toilet 6 times. Any questions about that one? All right. Did you use the same method to answer each question? Did we?
C.
We did. What did you do?
We didn't because we on number C, on the letter C,
Uh-huh.
we multiplied, and on letter D, we added.
So you added 2 of the equivalent ratios together?
Yeah.
6 to 2 and 12 to 4? Good. That does make a third equivalent ratio, and that is definitely a way you can solve it. Does everybody agree? Good job. I'm not going to write this out because you may not have used the same methods, and you may have used different methods than I did. It is up to you to explain what you did here. Any questions? Okay, next page. It is exactly the same with different numbers, so I'm going to give you 3 minutes to work on A through E. Go for it.
Okay, guys, listen up. So write each point as a ratio, gallons water used to loads of laundry.
Have a seat.
Again, I hate that they did this because they reversed the way you should have done it. Normally the ratio should be X then Y. But the ratios that they gave us, oh, there's the bell.
Bye, guys. Have a great day.
Take care, guys.